Okay, so in this video we'll take a proper look at what motion is, what we need to describe it, and the hidden structure within it. It actually took a genius like Isaac Newton to first invent an entire new field of mathematics to uncover it. But we'll get to that in due course. So let's start with our goal. Whenever we're looking at a problem in mechanics, so some objects moving around, what do we want to get as an answer? Well, simply you could say what we want is a full description of the motion taking place. What is a full description of the motion? What does it look like? We call the complete path that any object takes its trajectory. A trajectory tells us at which exact location the object is at any given time. Knowing this means complete knowledge of the object's motion. So this is exactly what we're looking for. We can describe the trajectory by drawing it or by describing it through a mathematical formula or even listing enough data points in a big table. Now, actually calculating this trajectory is a rather difficult problem in itself, and it will be dealt with in the next video about dynamics. Here in this video we will discuss what we can do when we already have this full trajectory, which is called kinematics, the description of the motion. The first thing we have to do when talking about motion is to precisely define what we're talking about. Put in the most basic terms, motion is the change of position over time. We've already mentioned trajectories and how they describe position over time, so I guess that makes sense. Okay, this means we will be talking about space and time a lot. And this is actually a really complicated topic, but the good thing is that for our purpose here, for mechanics, it doesn't have to be. All we need is our naive, everyday understanding of what time is and what space is. But to properly quantify motion, we need more than space and time. We also need to talk about velocity and acceleration. Velocity is defined as a ratio, a proportion of two already established quantities, distance and time. Intuitively, velocity is how fast you move. So not just how much distance you travel, but also in what time. In other words, the length in space in proportion to the length in time it takes to cover this. To calculate velocity in practice, you can, for example, use the difference in mileage divided by the difference in clock time. It's not strictly necessary that it's distance per time. It could just as well have been defined as time per distance. And actually this second definition also exists, and it's called pace and is often used by runners, for example.
That was 6.5 miles at a 7:15 pace. Had to keep it short this morning.
Acceleration is actually really similar in concept in that it is about how much your velocity changes over time. For example, if your car can go from 0 to 100 in 3.2 seconds, that is a change in velocity in a given time, so that's an acceleration. You could calculate acceleration by taking the difference in speeds shown by a tachometer divided by difference in clock time. Now, technically, there is no reason to stop here. We could also go and define the acceleration over time as a new quantity and then consider the change of this quantity over time again, and so on and so on and so on. And these definitions do exist. It's just that they have very few practical applications. It turns out that all we need to fully describe motion in general is location at any given time, velocity at any given time, and acceleration at any given time. When we look a bit closer at velocity and our mathematical definition of it, we spot an issue. The thing about velocity is it's calculated using differences between two time points. And this means what you're essentially doing is calculating the average velocity between these 2 points. How can you then calculate or even define the velocity at the moment? Not between 2 time points, but at 1 point in time. Let's go to an example for this. When you drop a heavy object from a high tower or building, it will fall down to the ground and will be accelerated by gravity. And as Galileo Galilei already figured out, the distance fallen grows with the square of time. And you can check out my video about free fall if you're interested in more details of this. More precisely, the distance fallen is given by s equals 5 times t squared, where s is the distance and t is the time. Let's assume the object hits the floor after exactly 3 seconds of free fall, having fallen 45 meters. But what is its velocity at that moment of impact? Well, easy you say. Just take the distance fallen and divide it by the time that it takes. And you get a velocity of 15 meters per second. This looks nice, but unfortunately it's wrong. That's just the average velocity for this distance and time. And it would only be correct if the object falling would fall all the time at the same speed. But that's not what the object does. It starts from rest and then accelerates all the way down to the floor. Okay, you say, let's calculate its average velocity for the final second of its fall then. Or the last half second. Or 1/10 of a second. Or 100th. Or 1,000th. And you see where this is going. We're getting closer and closer to the value of 30 meters per second. Interestingly, there is a mathematical operation where a ratio of differences can be made infinitely small. So you can calculate not the velocity between 2.9999999 seconds and 3 seconds, but just the limiting value at 3 seconds precisely. And this operation is called differentiating or differential calculus. And if you've been to high school, you have learned differentiating. Probably just didn't learn what it means. Now, there are rules for differentiating, but I don't want to get into those details here. When we use those, we get the following results for the velocity. So when s equals 5t squared, then the differential of s, which we will call s dot, equals 5 times 2 times t, which is equal to 10t. So the velocity v equals 10t. So at 3 seconds, the velocity is 30 meters per second, as we already deduced. And the same logic applies to acceleration. So all in all, it looks like this. Position differentiated gives velocity. Velocity differentiated gives acceleration. So once we learn to differentiate, the complete information about the entire motion is contained just within the trajectory. If you know the location at any given time, you can immediately calculate the velocity and the acceleration at any given time too. And this is the hidden secret within motion. And Isaac Newton first had to invent calculus to get there. And with this we have shown that to know everything about a motion is to know its trajectory. Everything else, like velocity or acceleration, can be derived from that. And these are the 2 essential points from this video. If we know where all things are and all things will be, we can make sure that the thousands of planes in the air and ships at sea never collide with each other. We can make sure that the spacecraft going to Mars actually makes it to Mars and doesn't crash land there. You know, unless somebody makes a mistake or uses inches or whatever. We can make sure that JWST arrives where it's supposed to, even though that's more than 1,000,000 kilometers away from us, and even signals with the speed of light take 5 seconds to get there. We can calculate whether comets or asteroids will hit the Earth, what the optimal angle is to throw an object as far as possible, and where an object will hit the ground when dropped from a great height, and with what speed. So obviously, kinematics is a very powerful tool. And next time we'll talk about an even more powerful tool. We will talk about how we can calculate a trajectory. And we'll find out that all we need is all the forces at work. This is called dynamics. And it is Newton's crowning achievement, the key point of all of mechanics.